this is a magnetic resonance and the basic principles of magnetic resonance and different kind of applications. And this will be important somehow because we will use that, these ideas, we'll implement them, we'll adapt them somehow to the specificity of the NV centers in diamond. Okay, so magnetic resonance is obtained by the superposition of two magnetic fields. There is a static magnetic field, B0, that is applied on the along the Z direction. And this magnetic field, as we have seen, will remove the degeneracy between the state plus and minus associated to this quantization axis. So this magnetic field sets the quantization axis, so a well-defined basis for the spin 1/2. And then we will superpose an oscillating magnetic field in the transverse direction. And what we'll see that this oscillating magnetic field can somehow flip the spin from state plus to any kind of other state. It can be minus state, or it can be, for instance, a coherent superposition of state plus and minus. And that's the purpose of the system. And we will see that this tool has led to a huge myriad of applications in physics, in chemistry, and in medicine. Okay, so we've already seen that before. So we did the calculation of the Larmor precession with two different approaches. The first one was classical approach. So it was simply the torque acting on a magnetic dipole associated to an angular momentum, if you remind. And we've seen also how this behavior can be obtained using the state plus and minus and their behavior in the magnetic field. So now let's consider the evolution of the spin under this Hamiltonian that, as we saw before, couples the magnetic dipole, which is an operator, mu, vector, to the static magnetic field. So we know how to write mu. Mu is simply gamma B0, gamma h bar over 2 sigma z, where sigma z is a Pauli matrix along the z direction, times B0. And what we have is coupled, if we decompose the state as C++ plus C minus minus, then we can write, we have two coupled equations for the evolution of C plus and C minus. There is a mistake here, of course, so I can maybe change it. Okay, it's corrected. Done. Sorry? It's okay? No? The slide, you mean? Okay, I don't know, because we see them here.
The recording it is not.
Ah, okay.
But it should be shared.
Because here, if we see them here.
No, it is on YouTube. It is not visible.
Yeah, I see. But me, from here, it's visible, so I guess it's somewhere else. Because if I see them on the screen here, I mean, everything is set on my computer.
Some loose connection.
Sorry?
There was some loose connection.
Okay. Okay, so we have those equations, and that can be solved very easily. We simply have C plus as a function of the Larmor frequency omega 0. I remind you, omega 0 is the Larmor frequency, and C minus here. So from that, we can easily get the evolution of the block vector. Remind us that the block vector is defined this way from here. So we see immediately that the block vector what's this? Ah, okay. I know. Let me see. Sorry. I have to remove that. Okay, so we see that this is the block vector here as a function of time is, if we compare this and this, we see that it is, we have this expression for the block vector. So we see that it is now processing as a function of time, depending on the evolution at the Larmor frequency omega 0. Okay, so we have the picture, the image of the behavior of the spin 1/2 on the block spheres, which is simply this precession at Larmor frequency. So now what we will have, if we come back to the state, we know from the calculation we did this morning that applying the static magnetic field remove the degeneracy between state plus and minus, and there's now a frequency difference due to the Zeeman effects of h bar omega 0 between them. And we apply the magnetic field, the oscillating magnetic field with a frequency omega. So there is a frequency difference or energy difference, h bar delta, between the resonance between state plus and minus, the Bohr frequency between state plus and minus, and the applied frequency of the magnetic field, of the oscillating magnetic field. What is important is that, of course, that the oscillating magnetic field is in a direction as a component which is perpendicular to the Z component. Otherwise, this field, if it's aligned on the Z axis, will have the same, will produce the same eigenstate. Those will evolve with time, but you cannot imagine to get a coupling from going, for instance, from state plus to state minus and vice versa. So we need some perpendicular component of the magnetic field to induce this coupling. And what we'll suppose also is that omega, if the order of omega 0 were close to this Larmor frequency. So now we have an Hamiltonian which is time dependent, which takes this expression, and we see that basically we have this matrix, and due to the coupling between the component, the transverse magnetic field, there is these now non-diagonal terms which are time dependent. So of course, what is not very helpful, as I state, it would be to try to search for new eigenstates, because those eigenstates will be time dependent. So it's not a good approach. So we'll use a trick for that. So basically, I can now write again the state in the Schrödinger equation, taking into account the state. You introduce it in this Schrödinger equation, and now I have to take into account the coupling between C plus and C minus due to the B1 field. So for doing that, we will try to see how we can solve it. And to solve it, there's a lot of different approach to do it. One possibility is to introduce a time-dependent basis which I put state plus tilde and state tilde minus that are defined as plus tilde is the state plus with a phase exponential e omega t over 2, and the same except a minus sign for state minus tilde. So now, of course, I can write the state of the spin 1/2 in this new basis, which is time dependent, with new components, and I can have the transformation linking C plus tilde to C plus and C minus tilde to C minus. Okay, I can now re-inject that into the Schrödinger equation, and then I have these simple equations. that are defined here as a function of the detuning between the frequency of the oscillating magnetic field and the Larmor frequency. And at that point, then we're going to do an approximation. And the approximation, I call that resonant approximation. You can also find that as rotating wave approximation, but I don't like so much this denomination. I prefer resonant approximation. The idea would be that we want to have a coupling, for instance, going to this point from C plus to C minus. And that will be induced by state B1. B1 will set the rate at which we will map, for instance, the state plus to the state minus. But then we have also these oscillating terms. And our approximation is to neglect these oscillating terms. We say this is far, if the detuning is small, that oscillates very quickly and on average will not produce any effect being able to map one state to another one. Okay, so what we simply do at that stage is to get rid of this point. This is an assumption, and after that, we have to see if this assumption is valid, for instance, by taking into account the evolution we will obtain using this approximation and trying to see if indeed we were right in neglecting this quickly oscillating term. So we neglect these terms. Now we have done a huge step. A big step, because now we have an equation, coupled equations, that with a term here, which is now time independent. And this is very important. So we have now a coupling, so delta and minus delta on the axis here, on the diagonal of the matrix, and non-diagonal terms, which will couple plus and minus states, and which is depending on which are defined by what we will call the Rabi frequency. The Rabi frequency is equivalent to the Larmor frequency. The Larmor frequency defines the coupling of the magnetic dipole with the permanent magnetic field, and the Rabi frequency is the same, but now coupling the magnetic dipole to the amplitude of the oscillating field. Okay, so now we can describe our two-level systems under this under time-dependent magnetic field structure by an effective Hamiltonian, and this effective Hamiltonian is time-independent. So we are back now formally to a Schrödinger equation for a two-level system with an effective Hamiltonian that is independent of time. For instance, like you might have already studied, for instance, by the coupling between the states of the ammonia molecule, where you say you have two states and you couple them through the tunnel effect. It's exactly the same now. And basically, we have this. And so if we see that, we are exactly in the situation that we studied before, where we have a spin 1/2. But now, instead of looking at its evolution under this time-dependent magnetic field, we now look to its evolution under this effective magnetic field that is non-time, that it's independent of time. And the components of the magnetic fields there is a component along the z-axis and a component along the x-axis. And somehow, if we come back now to the structure of the magnetic field, of the precession of the spin 1/2, we can easily determine the evolution of the system. I will try to do it, provided I have enough batteries. Let's see. No, I won't have enough batteries, sorry. Okay, so let's do it like that. You will try to follow me. So first, we can consider two different situations. Let's consider first the situation where the detuning is large. Delta is large compared to omega 1. Then the magnetic field is mostly along, so this will be the z-axis, okay? And I suppose that my point here is the plus state. okay, on the Bloch sphere. And what I would like to do is, for instance, to reverse the spin, which is going from the Bloch sphere pointing up to a Bloch vector pointing down, okay? And then that will be minus state. Suppose now that I have this state. My effective magnetic field on which this vector Bloch vector 1 will precess is mostly along the z-axis, okay, like that. So it means that the Bloch vector is doing something like that, okay? So the probability of going from plus state to minus state is very small, okay? Now, suppose now we are in a situation where delta equals 0. If delta equals 0, then we are in a situation where now this effective magnetic field is transverse, is along the x-axis. And what does the Bloch vector do? What does the vector Bloch, what's its evolution? Basically, it will precess. But now it's going to precess along my left arm, so it's going to do like that. So you see, it comes to the minus, there is a reversal, goes to the minus state, and then come back, then I have problems, to the plus state and back and forth. Okay, so I have using this Bloch sphere evolution and this effective magnetic field, I can very simply describe the time evolution of the system. And if I want, I can also solve all equations. This is exactly what we did before. And we can determine, for instance, very easily, the probability starting from state plus to go into the state minus is simply the projection of psi that will be modulus square of c minus tilde square. Okay? So I can plot those probabilities. So this is simply c minus. I can perhaps write it down here. Let me write it down. Yes, good. Okay. Okay. Now I write down the probability from going plus state to minus state, with the initial state being plus state. Okay. So this is simply this modulus square of this component for the quantum for the state, and I have this well-known formula, which is just describe the Rabi oscillation. And again, when you are far detuned, delta, for instance, is equal to 3 times omega 1. Then you have fast oscillations, but a small probability to go from state to go to the state minus. And this is the evolution that I mentioned. Fast precession with an effective magnetic field almost along the z-axis. Now, when I'm at resonance, delta is equal 0. So now the effective magnetic field like that, I have a probability of unity of going to the minus state. This is what I see here. This is the first part of the Rabi oscillation. Then I come back to state minus, to state plus, etc., and I see those Rabi oscillations. So that's what we see. Now, if I look to the probability, to the maximum value of the probability as a function of the detuning that I see here, depending of omega 1, this should be omega 1, I'm sorry, then the maximum probability of going from plus to minus is a Lorentzian as a function of delta, the detuning, and a width of 2 omega 1. This means that somehow, if I want to find the resonance, I need, for instance, this probability will become larger and larger if I increase the strength, the amplitude of the magnetic field. So this is a well-known phenomenon. It's called intensity broadening or amplitude broadening. I increase the driving field, the amplitude of the driving field, in that case B1, and then the transition become larger and larger and larger. And I can easily, for instance, find it. And then I will reduce the amplitude of the B1 field, and then I can point out, I can sort the resonance with an increasing accuracy this way. Okay? And this is well-known phenomena called, again, for power broadening, amplitude broadening, those kind of things. That's important. We will come back to that. You can, using this time evolution at resonance, we have two, we can apply a pulse of the oscillating field, and we'll define different type of pulse, and that will be also very important for the following. Pulse pi will transform, will map the state plus into the state minus. So there will be a reversal of the block vector, and if we now have the image of a magnetization associated to an ensemble of magnetic dipole behaving the same way, that would create a magnetization along the z-axis. I will call that longitudinal magnetization or longitudinal magnetic moment. Okay? So playing with the pulse P, it's somehow a way to take to, you can imagine that I have a kind of a magnet pointing up with north pole pointing up, and I reverse the magnet. Okay? Now I can also define a pulse pi over 2. A pulse pi over 2 will transform state plus into a superposition of plus and minus state, so that, for instance, we start like that, and basically we arrive in this direction, and this would be, for instance, the state plus plus minus. Okay, or depending on the evolution. And so I transfer now the block vector into the transverse plane, and now it's like having a magnet pointing up and transferring the magnet on an horizontal plane perpendicular to its horizontal direction. Okay? So basically, this is what we will do. And we will use that for a coherent drive of spin, and this will be important for measurement scheme with the NV centers. Okay, I can try to see this evolution now if I come back to my initial state, to the initial frame, sorry, because as I told you, there is two components. There is the precession at the Larmor frequency and the evolution at omega 1 that I mentioned before. So if I combine that, I can have the image of the block vector evolution in that, and which is basically this precession, and at the same time, a slow rotation going, for instance, to plus minus, to plus state, to minus state at resonance. And this is what I tried, what we observed in this very simple, what we observed in this very simple situation. We start with a block vector like that. There is a Larmor frequency, and at the same time, you see that the Z component is now turning, the component in the transverse field is like a compass which is oscillating at that frequency. Okay? And it's oscillating at, if I come back to that, when you see, it's oscillating at the Larmor frequency. This is important. Okay? So keep that in mind. Yes? So the rotate, that's somehow what people will say. The trick we use, we can say in this Larmor frequency would be like following the block vector, you know? And that's what people say, the rotating wave approximation. If that, I would be in a frame of reference in which I follow this natural evolution of the block vector. Does it answer your question? Important also is to look to those resonance frequencies. Suppose I have a magnetic dipole in a magnetic field of 1 Tesla. This is rather large magnetic field. And for instance, with an electronic spin, the Larmor frequency or the resonance frequency is around 14 gigahertz. So this is in the microwave domain. So if I want to play with electronic spin, I have to apply microwave. If I now want to play with protons or nuclei and the spins of the proton and the nuclei, then taking into account the difference of mass between the electron and the proton. We have almost 2,000 of different 2 to 10 to the 3 as a order as difference, and we go from gigahertz to megahertz. That means that now, if we want to manipulate nuclear spins, we have to apply radio frequency in this domain range. So that's the two type of wavelengths that we will require. Electronic spin will require microwave excitation, and nuclear spin will require radio frequency excitation. Okay, should change that. Basically, this. Okay, let's look now to first experiments. The first experiment on magnetic resonance was done by Isaac Rabi. And basically, he had the idea that, for instance, to measure, as we discussed this morning, to measure the spin of the proton, the nuclear spin of the proton, basically what you could do is use this resonance trick to know exactly where is the resonance in a well-defined magnetic field. Because if I take the formula here of here, sorry, it's here. No. Okay, it was before, I guess. Yes, here you see there is gamma here. And this gamma enters here in the magnetic field. So, of course, we have to find out by the condition of resonance, we can determine gamma very accurately, okay? And measure like that the magnetic dipole. So that was the idea, and I will show you how the experiment was realized. And it was realized with an accuracy much higher than what Stern could obtain by measuring the deflection of these hydrogen molecules inside an inhomogeneous magnetic field. It's somehow a much clever way, much accurate way to measure, to get the resonance and to determine the geomagnetic ratio and those parameters. And then that was done in atomic beams, so it's complicated machines that you have a beam of molecules, for instance, and you play with the spins associated to these molecules. And now there were two breakthroughs. The first, you would like now to do it, but not with spins embedded of individual molecules propagating in a molecular beam, an atomic beam, but you want to do it, for instance, with molecules in an ensemble in a liquid or solid of those kind of systems. And that was first demonstrated by Zavoysky in USSR, where at the end of the Second World War, where he had his lab transferred from Moscow to Kazan, and he was the first to observe the magnetic resonance of electronic spin in the solid state. That's electronic spin. And basically what he was doing is making the absorption of just sending a microwave onto the system and trying to observe if there is some absorption of the microwave field by the spin resonance, the spin flip-flop induced by the magnetic resonance. And independently, there were two experiments realized on the East Coast and West Coast just after the Second World War in 1946 by Felix Bloch on nuclear spins, and at the same time by Ed Purcell in Harvard by also nuclear spins. And they got Nobel Prize from these results and the breakthrough it led. And also Rabi got the Nobel Prize, and this was a citation. By this method, Rabi has literally established radio relation with the world of the atomic nucleus, which is a very nice way to describe the achievement. Okay, so I will try to give you a little bit of idea of those experiments. The first one, the Rabi experiment with a molecular beam, it's basically you use spin preparation and spin detection using Stern-Gerlach-like apparatus. So basically, you have two Stern-Gerlach apparatus, and you inverse them somehow. And somehow, if you do not do anything, the spin will behave on a way, and the second apparatus will compensate the behavior the other way. So somehow, this compensation is you associate the spin up or down to different paths in the systems, and basically you recombine those paths on the detection point. Okay, and you measure the number of molecules or atoms you have here. Now suppose that in meanwhile, you put here a cavity here, which is resonant at a given frequency. This means that somehow the state which is plus here and which would be would have this trajectory here, now will have the compensation, between the two parts of the apparatus here, the two reversed apparatus, will not work. So it means that since the compensation is not working anymore, you will lose atoms from detector D. And basically, it's what you see in this resonance signal, where you see the number of molecules being constant, and then at resonance, it suddenly drops, and after it reappears again once you are far from the resonance. The trick is not to scan the microwave or the radio frequency of the frequency. You just fix it. You build to have a strong magnetic a strong resonance, a strong drive of the magnetic resonance. You make a resonant cavity at a given frequency, and what you tune is you tune the atoms. You tune the levels of the spin 1/2. And this is done by just changing the magnetic field, and for that it's very simple. You have external coil, and this external coil, you apply a current in that, and by changing the current in the coil, you change the magnetic field, the static magnetic field B0. So you tune the Bohr frequency omega 0 at a given omega 1 that is fixed, and a given frequency omega of the driving magnetic field, of the oscillating magnetic field. Okay? And using that, there were beautiful experiments. For instance, on the molecule H2, instead of having something quite broad associated to the protons, you could see actually different resonances, and all these resonances were describing the interactions between in the molecules. And you can see actually the different state associated to spin, nuclear spin. There's two protons, so you have nuclear spin, total nuclear spin capital I equal to 0 or capital I equal to 1, and this is what you observed. You observe different structures of those spins associated to that. So that led to the development of radio frequency spectroscopy for molecules, and you could have now, using these tools, there were a lot of experiments that were done to really probe the inside of a molecule. For instance, how the spin will be coupled if you take into account, for instance, the vibration of the molecule or the rotation of a diatomic molecule that would appear in the coupling of the nuclear spins inside the system. So it was really developed as a very powerful tool to go to investigate, to measure, to do the spectroscopy of molecules. Okay, now let me point something which is quite important. What is important is, should I do it now or never? No, maybe I will do it here. Yes, I will do it here. So maybe I should change that. Sorry, there are still some reminiscence of French. One important point is that when we do this, now what was the problem? The problem, if we want to apply that to a solid or a liquid in which you have a lot of nuclear spins embedded. The difficulty in that case is that you cannot prepare the spins in a given initial state. In this experiment, the first apparatus somehow prepares the state, the molecules in well-defined quantum state plus minus. Okay, and you, like in the Stern-Gerlach experiment, you correlate those spin states to trajectories inside the apparatus. This is not something you can do when you looked, for instance, to a piece of liquid or to a piece of solid. So the problem is that then the thermal equilibrium, you can only rely on the thermal equilibrium at temperature T to create a difference between the population of the state plus and minus. Because if this population are equal, there will be the same amount of molecules doing that compared to molecules doing the opposite way. So the two will compensate and you wouldn't get any signal. Now the trick is that there is a slight difference due to thermal equilibrium. And if you take into account the frequency difference, for instance, which is obtained in a magnetic field around 1 Tesla, this is what I mentioned before, at ambient temperature, 300 Kelvin, this difference of population is very tiny, very small, 10 minus 5 orders of magnitude. So it means that you have to detect a signal which will be very weak. But the good point is that you work with macroscopic sample that embeds a large number of spin. So somehow you compensate this tiny difference between the population by investigating a large ensembles of spins. And that allows you to get a macroscopic signal, a detectable signal. But that was quite difficult. So you could do it, for instance, that's what first it was developed with electronic spin, because somehow the energy difference is larger. So this difference of population, it's of course much higher for a thermal distribution of electronic spins compared to the thermal distribution of nuclear spins. So, and an important point also, if you want to increase that, of course, to enhance the signal, you have basically two possibilities. The first one is to increase the static magnetic field amplitude, B0, because then you will have a larger difference of energy between those two states, okay? And the other possibility is to cool down, is to cool the system and to work at much lower temperature, at cryogenic temperature, and then you will also enhance the effect. But if you want to do spectroscopy under ambient condition, somehow you have to work with that. There will be trick to improve that by using different schemes to pump the system in one of those well-defined states. And we will see how this works with the NV centers. And with the NV centers, we'll see that optical pumping will allow you to prepare the state into a given state of the spin. That was found also in optical pumping scheme was found in the 60s by Alfred Kastler and Jean Brossel. And Alfred Kastler got the Nobel Prize also for this use of the optical, for the invention of optical pumping, for improving the sensitivity of NMR and EPR detection. Once we have created a population and we release the system, of course it will come back to this thermal equilibrium, and that will occur in a time duration which is called the T1 time, and this will also be important for the following. Okay, now what I want to see, okay, I realize that I can do the experiment, compensate this slight population difference by looking to an ensemble, and then I have two approaches. The one that was pursued by Ed Purcell and his team was to say each time I do a flip-flop of the spin, there is a radio frequency photon that has been absorbed. Okay? So I lose energy of the system. I transfer the spin from a lower energy state to a higher energy state. So somehow the difference of energy has to come from somewhere. It has to come from the radio frequency that is applied on that. So what you will do is simply send a radio frequency signal using, for instance, coaxial cable or something like that, and in and out, and you measure the input energy, the amplitude at the input, and you compare it to the amplitude at the output. So it's just a frequency difference. And you do it in a way with sensitive enough that you can really measure the absorption. And of course, you do it at a given frequency because you will have, like always, you will build a resonant cavity at a given radio frequency signal. And now you tune around it the Larmor frequencies of the spin by applying a static magnetic field, and you control the amplitude of B0 of the static magnetic field using current in coils. And then they could see that that was done with glycerin, if I think, and they could observe the signal exactly where it was expected. The other approach was a little bit different. The other approach, led by Felix Bloch, is to see the spin really as a magnet, and somehow have oscillating magnet, if I remember, and to detect the oscillation of the magnet on a pickup coil. So you will have a pickup coil. So if I come back to that scheme here, and I have the image, you see that the transverse magnetization is doing this, okay? Turning like that. Suppose now that I put a small coil on the side, and I have this magnetization like doing that. What I will see is that the magnetic flux along, which goes through this pickup coil, will be modulated at the frequency omega, at the Larmor frequency, okay? And so this, you will have a modulation of the magnetic flux through the coil, okay? And if I have this modulation, I have an electromotive force that I can detect by the voltage on the coil, appearing on the coil. Okay, so the idea of Bloch is try to detect this motion of the transverse magnetization using this system. And this can be done, so it's the signal here. And maybe we hope that on Thursday, we will show you a very simple implementation of the scheme. So we will show you a basic system that can be used to detect the spin resonance for an ensemble and play using that along the Felix Bloch approach. Again, what's important to remind, it's the fact that these measurements are not projective quantum measurements. It's not like, it's a measurement that is built up on an ensemble. So you have to repeat it many, many times, and then you build the signal, and it is this signal that you will detect. It's not a single shot experiment. I cannot say in those experiments, my spin is like that, and clack, I've been able to do that. So there is a great step to do to go from those kinds of detection to a real single shot measurement where, for instance, you would like to play with the spins and do, for instance, a gate where you will control, for instance, one spin state will control another spin state, like in CNOT gate or those kind of things. And I will show you how this could be possibly done. So the detection is done on is a collective signal. And built from a response of a very large number of molecules. And this can be described using the density matrix. And that also can be used to see the evolution of the spin, taking into account the environment or the other spins fluctuating nearby. And I will try to discuss that. Okay? What can you do with this tool? So there's really remarkable applications. For instance, if you are sensitive enough, you can look to the protons inside the molecules. For instance, let us consider the molecule of ethanols. And this is a structure. You see that each protons will see different environment, different electronic cloud around him. So those protons on the side of the ethanol molecule will somehow are equivalent, okay? Whereas these protons on the other carbon atoms will see the screening will see the influence of the oxygen atoms. And this one here will see the influence, a very strong influence of the oxygen atoms. So all this now, if I apply the magnetic field the magnetic field that is applied, the static magnetic field, will be shielded by the proton electronic environments, by the electronic cloud of the molecules. And that will shift the resonance by tiny amounts, typically relative shift of the order of 10⁻⁶. So we call that usually, it is called the chemical shift. And the chemical shift is a characteristic of the molecule used. And you can determine where the protons are located inside the molecules. And you can also count how many protons are equivalent in that. And this is exactly what is observed here. You see different of resonances. A strong one, which is associated to these 3 protons. At another frequency, we see another resonance with weaker intensity, which is associated to these 2 protons, and this one, which is associated to the proton close to the bounded directly to the oxygen atoms of the molecule. So this is a very important tool, and of course, chemists have used this tool more and more efficiently to really investigate the structures of molecules that they are able to synthesize. One of the goals of NV physics is somehow to use the NV, the magnetic resonance of the electronic spin of the NV signal to try to see by hyperfine coupling we can detect somehow this kind of effect directly on the NV signal. And there were beautiful experiments, but not yet at the level of sensitivity that is competing with this kind of system that have been developed now up to extreme sensitivities. Okay, if we want to do that, I told you there is something which is the power broadening. Of course, if we want to find first the resonance, you boost the amplitude of the B1, the oscillating field. Once that allows you to set the system, but then, of course, it's broadened. So there's a nice way to do this spectroscopy that was found and developed, already found by Bloch, and then developed very intensively in the 90s, 80s and 90s, especially, and it led to the Nobel Prize to Richard Ernst, the development of this technique, which is called Fourier transformed NMR spectroscopy. So instead of continuously applying the radio frequency field, I will get rid of the power broadening. What I will do is that I start from the system in equilibrium, then I apply a pi/2 pulse. The pi/2 pulse now will create magnetization on the transverse plane, as I've seen. And what I do then? What I will do is now I release the driving field. There's only the static magnetic field. So I have the initial magnetization is like that. There is the static magnetic field along the z-axis. What does the magnetization? It just rotates in the xy plane. We are back to the situation that I described previously, where there was, this magnet spinning in the transverse plane. So if now I set a pickup coil in this way, I will get a signal that will circulate due to the modulation of the magnetic flux through this pickup coil. And this is what you see. You see this signal, but of course, there will be decay process that I will discuss maybe later, perhaps not today, but later, that will have this precession to decay, that will lead to a decay of the precession. And the signal is called the free induction decay time. And using a Fourier transform of this signal, I can now determine the frequency very accurately. And this is a frequency without any power broadening effect. So it's only the pure limitation of somehow the scrambling of the coherent oscillation rotation of my assembly of dipoles. Okay? Is it clear? So this is mostly what the basics of magnetic resonance that we would like to do. And if I look to this decay, we can associate different time scales. So basically, this is the transverse oscillation, okay? And usually the signal we will get will decay in this way. And you have to take into account different possibilities. One possibility is the fact that the magnetic field in which all my NV centers, all my spins are located can have differences. It's not perfectly homogeneous. It means that then I have different spins that precess, but at different frequencies. And of course, when I start, they are all in phase. But progressively, they get a dephasing, and at the end, everything, the signal is averaged to 0. Okay? And that occurs within a time scale that I will call T2 star time. Okay? So T2 star is the scrambling time due to the addition of spin oscillation in this inhomogeneous magnetic field, so that the precession these spins are doing occurs at slightly different frequencies. And adding those contributions, after a time, you have random phase that occurs due to this difference of frequency differences, and that gives the signal to disappear, that produces the disappearing of the signal. Somehow that's due to the apparatus itself, but I will try my best to make the magnetic field as homogeneous as possible, but there will be still some inhomogeneity. I cannot do something perfect. But nevertheless, suppose I do have something perfect. Then there is still other things that can remove the spin, that can lead to a decrease of the spin oscillation, which is, for instance, the interactions with other spins. There can be, for instance, other spins in my material that somehow will flip-flop randomly, okay? And then that will create a fluctuating magnetic field onto a given spin that I'm looking at. And this process will now, when I add them continuously, will make the signal to decay. Okay? And this is the T2 time. We also define the T1 time. The T1 time is just the time that the signal takes to come back to the equilibrium state. When I do nothing, the system will go back to the equilibrium state for the population. And usually, in condensed matter, we have these orders of magnitude. T2 star will be smaller than T2 and smaller than T1 time. And if I take, for instance, the NV centers, the T2 star will be around can be around a few microseconds. The T2 can be increased up to something like 100 of microseconds. So there is typically a factor of 10 between them, and the T1 time can be up to millisecond time. And if I cool it down, I can even go to higher time, longer time. So typically, there would be an order of magnitude of 10 in these parameters under ambient conditions. We will come back to that and illustrate that later. Okay, I think I'm going very quickly. Nevertheless, okay, once I'm here, of course, this is something very bad, because it tells you that you are limited in measuring the spin resonance here by the T2 star. Okay, so somehow something not intrinsic to the system, but something related to the quality of the magnetic field, of the static magnetic field you apply on the spin assembly. Okay? So if I want to get rid about that, there's a beautiful trick. And the beautiful trick was discovered by Erwin Hahn in the 50s, working in Berkeley. And the trick is the following. What I mentioned before, I will come back to this system. Okay? I have that. So we only look to the magnetization that is depicted in the plane. And you imagine that there is an assembly of spin, and all these spin have this motion like that, but at different frequencies. So the image taken to explain what Han imagined is the following. Imagine we have runners on a stadium. Each runner has its own speed. You cannot change it. And somehow this is associated to where the spin are within the magnetic field. Okay? Now there is the starter here, gives the signal so that each runner start together. All will start together. And they run, but at different frequencies. And what you see is that when you go here, you see runners occurring from here to here to here, and they are completely dispersed on the running track. Now, the starters send a new signal. And then the runners know that they have, at the same speed, to come back to the initial point. So they turn, and they go back the other way. And of course, if everything occurs at the same speed, they will come back all together at the same time in front of the starter. So somehow you have restored the order that was somehow hidden inside the system. So you just need now to find a way to apply that on our assembly of spin. And this can be done by applying pulse, a pi over 2 pulse. A pi over 2 pulse will somehow inverse the spin state. It will inverse plus to and minus 1 minus state. So somehow it will have exactly this effect. So what we will do is this. We start by a pi pulse over 2, a pi pulse, sorry, in between. So I start with a pi over 2 pulse. The pi over 2 pulse, as I mentioned, is create this in-plane magnetization. And when it processes and it decays within the time T2 star. Okay? Then we have no signal. But the spins are still continuing, and they survive until T2 time. Now, within the T2 time window, I now apply a pi pulse. The pi pulse transfers the state plus map into the state minus, and the state minus is mapped into the state plus. That's equivalent to saying to the spin, go back. Okay? And that's what they do. And basically, they refocus at a time which is 2 times the time difference between the initial pi over 2 pulse and the pi pulse. And then progressively, you see the signal here reappearing. Of course, it will decay. It will be within a window of the order of magnitude of T2 star. Okay? Not far. But then this echo signal, if now I increase that, can survive until you reach the limit of the T2. Okay? And now I can really measure the intrinsic, somehow, lifetime of the spin coherence in the system, just by doing this scheme. And this is very important. This has been really a key tool for NMR spectroscopy because it allows you somehow to address different spins inside the system without the constraint of the T2 star time. And then there was very complex sequence. I will perhaps illustrate that later on, where somehow if you want to address a specific coupling for instance, between 2 spins, then somehow you can design a pulse sequence that will be adapted to this pulse sequence. So you can have a complex pulse sequence. That's the simplest one, but you can now improve that to somehow have more and more efficient investigating tool to address couplings between spins. This signal? Okay, I'll come back to that. This is the signal I mentioned before. Okay? You agree with that? So I see a signal, a decay, which is disappearing of the order of T2 star. But what I would like to mention is that the spin are still processing, all at their own frequency difference, at their own frequency. So what I do then by a pi pulse is that I reverse them. And the reversal of the spin obtained after the pi pulse will now lead to a refocusing of all those spins, so that at one point they will progressively recreate the initial magnetization. And this is what you see here. You see an echo signal, which is a refocusing of all the spins at a time which is simply 2 times the duration between the initial pi/2 pulse and the pi pulse that was created here. And this is exactly the image that I mentioned here. The runner on the running track starts with different speed. They spread all over, so the signal, you cannot say which is which, okay? And at one point, they run the opposite way, and they refocus at a given time, which is simply 2 times the duration between here, the initial signal, and the pulse signal that was telling them, go back. So it's exactly this idea. And you can do the mathematics. It's not so complicated. We can perhaps do it tomorrow, where we can really see all these kind of things. Okay, maybe tomorrow we can do that. Maybe you want to, because mostly I finished, I was too quick. Or I won't have many slides.
Maybe we take a small break.
Okay, we take a small break, and then we'll come back. But we will almost have finished. Okay, let's do that. Good. So yes.
There is a small P outside.
Sorry.
So the state got conjugate now. Whatever the initial in-plane state it was, let's say psi. So
Yes.
applying the pi pulse, I'll be doing the conjugate of the state.
Exactly. Exactly.
Maybe that's how it is done.
Exactly. 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 It's exactly that. And we try to see that. I hope that on Thursday we will be able to show the demo experiment on that. It was a very basic scheme, so we hope to be able to see it, to show it.
So let us take a small break.
Yeah, sure, you're right. Because if there is a tea, just go and take the tea.